Okay. بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so today we're going to continue with Numpy arrays and we'll talk about reshaping and resizing. So basically reshaping and resizing are going to change, let's say, the structure of the Numpy array, but in different ways. So okay, now this is about reshaping. So we use here the function reshape to change the shape of an array, but here without altering the data, without changing the data of the array. So what does it mean? If you have an array like this, look 1, 2, 3, 4, 5 until 9, and you reshape it to 3 by 3, you're going to have the same element, not changing to the elements. And we did one example, but here I wanted to explain a little bit the foundation. And of course, we need to have compatibility between the two dimensions. The original dimension, which is 1 by 0, or sorry, 9, 1. So 9, okay, 1 row and 9 columns. It's one dimensional array. It can be considered both. And this one, it's also 9 elements, but it's arranged 3 by 3. If you do it 2 by 5, it's not going to work. Okay, so look at the reshape. All the elements are here. But now, if we do resize 2 by 5, it will work. It will not work with reshape, but it will work with resize, because here it's going to make the same element and then we'll wrap up, okay, starting from the first element, second element, and so on. And you can test it in the Jupyter notebook here. Okay, let me make reshape. Reshape versus resize. Look now. This is the example. Let me increase a little bit the size. Now imagine that I do reshape 2 and 5. It will not work. Okay, it's already here. It made an error. I don't know why it doesn't execute. Okay. Cannot reshape array of size 9 into 2, 5. 2, 5 contains what? Contains 10 elements. Okay, now 3 by 3 works. Can we make it something else? Okay, not 3 by 3. Okay, 3 by 2 it will not work because it's 6 elements. Okay, because 9 it's only 3 by 3. But let's make, for example, 12. Okay, let's see, 12 elements. Now 12 elements, I can do it what? I can make 4 by 3. I can make 2 by 6. Yes, it has to match the size, the overall, the number of elements. Okay, number of rows multiplied by the number of elements would be the same. Okay, I can do 6 by 2. And look now, we'll have 6 rows. Now, regarding here, look at the resize. I put the number of element here 10 and I have 12. So no problem, it will make from 1 to 10. Now, if you make it 2 by 7, it will go. No, for resize it goes. Resize, it will change the size. Not only reshaping, it's reshaping plus changing the size.
This is reshaping.
Yes.
What if we reshaped it to a size that it doesn't have enough elements to fit in?
Which one? Reshape?
Yeah.
Same thing. It must have exact number of elements.
If it doesn't, then it will
Resize it work with many elements, or look, for example, I will make it only one like this. For resize, it's fine. Resize. But reshape, no. Reshape, it must have the exact number. You cannot have a different number. Okay, now if I make it even 3 by 7, will still work and will add elements. So this will even change the memory size. Okay, but it's more common to use reshape in machine learning. Okay, so it starts from 1, 2, 3, 4, just looping over the same values. Okay, so the new shape must be compatible with the total number of elements, and the application of reshape, it will create a non-copy view. Okay, so what does it mean, a non-copy view? It will not create a new array in the memory, it will change the array itself. And I will explain you the difference between deep copy and shallow copy, which is a concept in programming languages and also applies here. Now, using resize, it will alter the shape and the size both together in place, and we use numpy.resize and we provide the array and the new shape. And resize here, it will modify the array itself and can lead to the loss of data if the array is shrunk, or additional data if we add more elements. So the size of the array, even in memory, is going to change. And this here presents the differences between resize and reshape. Okay, about data integrity, reshape usually a view, changes may, reshape changes may affect the original data, and resize, it will alter the array itself. So in terms of memory, it's more efficient because it will not change or will not make any copy of data in the memory. However, for the resize, it can increase the memory usage due to additional data or less data depending on the new dimensions. Now there is an important also topic, which is the deep copy and the shallow copy. So just in short, a deep copy is going to create a completely new object in the memory. And the shallow copy is going to create an object. Okay, the first one, the deep copy, create an object and even new data in the memory. However, with the shallow copy, it will just create a new object, but will make a pointer to the reference data. So let's see here what happens. We use the copy or dot copy to copy the elements, and dot view to create a reference, a new object that refer to the same data in the memory. And let me illustrate this through the example. Look now, we have an original array. Okay, and here I'm going to create a deep copy of the array, which is using the method dot copy. And here I'm going to create a shallow copy of the array. Yes. Okay, which should be here dot view. Let me keep this. Okay, but so here we have dot view. Okay. Look now. I created a deep copy and the shallow copy. Now, when you see the result, you don't see any difference. You say, okay, well, what's the difference now? Now, the difference, we can actually monitor this by looking at the ID. Now, usually, if you want to see whether the memory is the same or not, we can see the memory reference. So, we usually expect that the ID of the original one should be the same as the shallow because we don't create a new object in the memory. But actually, is it the same?
No.
It's not the same. So here with Numpy, the shallow copy operates a little bit different because it will in fact create a new object but will not create new elements. واضح؟ And an object الآن created, لكن it will point to the same elements into the memory locations. However, the deep copy, it will create a new object and copy the entire elements into the memory, so it will duplicate the memory. Yes, so in order to see this, okay, there is a special function. It's this one. np.shares memory. So this will return either true or false. If they share the same memory, it will return true. If they don't share the same memory, look now. I do the same thing. This is a deep copy, and you can a deep copy. You can do the shallow copy also using similar using this notation. And now let me execute this one. So indeed, I have different IDs, but now comparing the array. Okay, this is deep. Comparing the array and the deep copied, they don't share the memory. And comparing the original array and the shallow copied array, the result here, it's true. It means that they share the same memory. Of course, because it will create a new object, but this object will send a pointer to the same data. Okay. And you know how you have the data structure course, so it's all a matter of pointers within the memory space. Is it clear? Okay. And here you can see you will have exactly the same after. And the impact of modification also, so imagine that we change 200. Look at this one, the impact of modification. Now I make a change on the shallow copy of the array. What will happen? Tell me. I change the value on the shallow copy of the array. What will happen to the original array? Will it change?
Yeah. Because the same reference.
Because yes, it's the same reference. Now this is before after modification. So this is the original array after deep copy modification. So look, when we did the deep copy modification, nothing changed. When we did the modification on the shallow array, it has changed. Okay, it was 200. So changing the deep copy will not make any change to the original copy.
Question.
Yes.
What's the point of shallow then?
It's just to create another reference. So sometimes you want to create a reference to use it as a mirror of the original one. It's not very common, okay, but it's a possible way. Yeah. Okay. So this summarizes the differences between both. The deep copy, it creates a new object, and the deep copy makes an entirely new object in the memory. And there is no shared reference. The new object is completely independent of the original one, and it's completely independent in terms of modification. If you modify the deep copy, the original copy will not modify it. So everything is different when we use the shallow copy with view. It will create a new object, but at the same reference, and we used np.share memory to monitor this. And also it has an impact of modification. So if you alter any value on the shallow copy, it will also reflect, okay, on the original object. So slicing also, it does a shallow copy. When you slice, for example, you slice an array, any operation that you do on the slice, it will be affected on the original array. Okay? Yes. And this is why, if you have observed here, we can do a shallow copy using just slicing. Here we take all the elements. So whatever the slicing you will do, any modification on the slice, it will be reflected there. And this is very important because sometimes you take a slice and you say, oh, this is an independent value. Now, if you want to make it independent value, you have to make dot copy. So you copy this slice into another memory space. If you want to do operation on that slice, but not on the original array. Is that clear? Okay. Yes.
If the shallow copy shares the same memory as the original, wouldn't that mean that affecting the original could affect the shallow copy? Therefore, it can't be used as a sort of copy of it, more as just a reference.
I didn't get your point.
They share the same memory.
They share the same memory, yes. Any modification from this guy will also reflect on the other.
Yeah, so it's just a reference.
It's just a reference, yes. Yeah. It's just a new reference to the same memory space. Okay? Same reference to the same memory space. Okay. One good feature in Numpy arrays is that you can input and output to the file. And this is very useful, especially, for example, in computer vision. Pixels are usually loaded into a Numpy array, so we can do any kind of processing. Like, I want to train on a neural network, I need to convert an image into a Numpy array. So usually, we load these values from the file into a Numpy array. And we can also save. You can have a Numpy array and save all the values into a file. So later on, you would like to load the same values and work with them. So file input and output operations are essential for storing and retrieving array data. Okay, so you can have persistence of your data after you do processing. You can save them and retrieve them afterwards. And it's commonly used in data analysis, machine learning, scientific computing. And this is an example here. We start by writing data. So for example, imagine that you have a Numpy array. So in practice, this could be an image, for example, or any kind of data that you load from a file to the memory. And now I would like to save this image. I can use numpy.save text. So we have two options here to save text and save. Okay, and save Z. This save and save Z, they save it as a binary file, and save text, it save it as a text file. And basically you can load the same data afterwards. So this is a text file now. I applied this code or this script. I used np.saveText here, and later on I loaded the text. Okay, so this is the text representation of the file. Okay, so this actually encode these values 1.5, 2.5, 3.5. They are encoded into this file. Or we can use .save here. So yeah, save Z. If we want to store it into a binary file, and this is here the representation. Okay, so this represents the same data. One is textual data, and the other one is a binary data. So usually we will save in binary data. Why? Okay, first of all, more secure, and
It takes less space.
less memory space. Yes. So almost 100% of the time we will store our data as such. Yeah. This is more compressed and more efficient, even for loading and memory usages as well. especially when you have very large data set, it's going to count a lot. Okay, so we can reduce from gigabyte to megabytes instead.
Sir,
Yeah.
can we save to an existing file?
Save what?
Save, let's say, the array to an existing .txt?
Yes, yeah, you can. You override it. Okay, yeah. And you can here specify, for example, what's the delimiter in the text file. For example, I put comma here. It's like a CSV file. You save it like a CSV file. And then you can load it.
ستحتاج إلى فتح قفل هاتفك أولا.
What's this? Okay. Yeah, that's pretty much it. So you have, it's very intuitive. np.save will just save it as a binary file like this. Okay, so to read the data, you can use load txt or gen from txt for handling missing data and complex structure. Okay, so this is how to use it here. You can use load to load from binary, and load txt is to load from text representations. You have here a code that you can try. Okay, so the same code here. You can save it, of course. Now here it will save it into the same hard drive of the virtual machine. Okay, you can save it on your Google Drive, but you need to import from Colab the Google Drive and save it to the right path. Okay, and this is the same loaded data now. This is the data loaded from the Numpy NPY file. Okay. So how data is actually stored in the memory? Do you know the different storage patterns of, for example, arrays in the memory?
The one element in the array points to the next element. The memory is right.
Yeah, that's like the linked list or something like that. Yeah, there are different ways. But in terms of performance, as already mentioned, it's always preferable that the elements are contiguous. It means they are collocated one after the other. So their retrieval will be much easier. And this is how Numpy actually managed the memory layout for the storage of a Numpy array. So basically we consider a Numpy array as contiguous memory blocks. So for example, this could be a Numpy array of 4 elements. So when they are stored in a contiguous manner, this will provide much better efficiency in processing and also in storage. And this is non-contiguous memory blocks of 4 bytes. Okay, so in principle, in operating system, you should learn about this type of storage in the memory. And contiguous patterns, they are of 2 types. We have the C contiguous and the F contiguous. So what is the difference here? So first of all, C contiguous is the way that C and Python structure their data in the memory, and F contiguous is how Fortran structure the data in the memory. So C contiguous, it means that the flow of the data is row-based. This is what we call row-based contiguous allocation. Yes. So we go from 1, 2, 3, 4. So this is the first row, and then we go to the second row, we go through the element and so on. This is the traversal. It manages the traversal of data into the memory. For the F contiguous, it actually follows the, it goes column by column. Okay, first of all, it goes through all the rows, then the second column, then the third column, and then the fourth column. Okay, so this is one-dimensional array. It's basically C and F contiguous. There is no columns. There is only, you can consider the one-dimensional array as a column or as a vector, or as a row. Now for two-dimensional array, it's like this. For three-dimensional array, this is how it is stored. Okay, so we have 4 elements, and then the next 4 elements, and then the next 4 elements. And this is how it flows. In F contiguous, it's a little bit more complicated because it will store by columns. So look now, it will store this one,
0, 1, 2.
and then it will be, the next one is blue, the next one is green, and then yellow, and so on. Okay, so look, jumping from one element to another is a little bit more tricky than the C contiguous configuration. And now this is how we can, so how this is helpful in Python, we can actually determine what is the arrangement of elements in a Numpy array. And look at this code. So you create an array, and then you transpose the array. You know what is a transpose, okay? So, and here we're going to assess the first matrix dot flags. So dot flags, it will tell you what is the contiguous pattern of that array. And then we will do the same thing for the transposed array. It will return true if it is C contiguous, and it will return false if it is not C contiguous, F contiguous, I mean. And look now, this is the original matrix and this is the transposed matrix. So the first one, by default, it's true. And this is how Python actually manage the allocation of memory for NumPy arrays. But now when you do the transpose, it becomes false. So why is this?
Because the row became the columns.
Yeah. Look now, this is the array, 1, 2, 3, 7, and this is the transpose. Okay, and both of them, they are allocated as such into the memory. Okay, so look now, for this one, you go first row, second row, third row. For this one, look, this is the first element, I jump, I go to the second element, and jump again, go to the third element. So it is not C contiguous. Okay, the same representation, but what is the difference is on the way, the contiguity way. نسميه التواصل, الوصل between the different elements. And this affects the performance. Now you can say, what is faster? Is it to use C contiguous or F contiguous? The response depends on the operation. Okay, you cannot say that C contiguous is always faster than the other one.
So when you transpose a matrix, you're not just changing the shape and elements, you're actually changing the way it's stored in the memory.
Yes, we actually don't change. Look, I put you here a very, very nice reference on NumPy array. I took from that reference, and here it shows you what happens when you do a transpose in the memory itself. Okay, let me go to this tutorial. It's really amazing. Now, this is a matrix, and this is you made the transpose of that matrix. That's clear. But what happens in the memory actually? Nothing. It's only the pointers, the way how they will be changed. Okay. So basically, when you do, so when you have the original matrix like this, you have C contiguous. Okay, and this is the representation in the memory. When you do the transpose, you will have the same representation in the memory. No elements is going to change its position. What changed is the pointer. So here the pointer, we will have a stride of 1 for the column and a stride of 4 bytes for the row. And here we have a stride of 1 for the row and a stride of 4 bytes for the column. Just the stride is going to change between the column and the row steps. This is how the transpose is made. Don't think that the transpose is going to change the way how elements are organized, but it's going to change this metadata that will tell how to do the traversal over the elements. Okay? Yes?
If you're still using pointers, then what's the use of having contiguous memory? If you're still using the pointers?
Yeah, the pointer. Yeah, the pointers. It's the way on how to do the traversal. Okay, and contiguous. It's with respect whether they are contiguous with respect to the row or with the columns. Did this respond to your question?
I think
What is your question?
the question is, it's saved in the memory as contiguous blocks because it's faster, right?
Yes, this contiguous block, you don't traverse it into the same way whether you have this matrix or its transpose. So F contiguous and C contiguous will tell you how you will traverse that memory. Okay? It's not because you have the same contiguous block of data that you will do it in the same way. Okay? The order of data is different and is captured by these two pointers. And you will have as many pointers as the number of axes and as the number of dimension that you will have into the matrix. This is the implementation on the traversal on the memory itself. Okay? Because at the end, as you said, as you have seen in the data structure, everything is managed by the memory. To which next cell in the memory you're going to jump. Okay? So in the linked list, for example, you will have traversal forward and backward. Okay? In some other list, you have only forward, and so on. Okay? So here, this is the way on how we do the traversal on the memory space with respect to the NumPy array. I invite you to look at all this reference in detail. It's one of the best illustrations that I find, okay, on different type of operations on NumPy array and even their Python script. Of course, the NumPy memory layout, and this may respond to your question, it has a big impact on broadcasting, on vectorization, on the effect of iteration. For example, here, for iteration, C contiguous arrays that are row-wise are faster, okay, than F contiguous arrays. Okay, that's one of the differences, for example, between both. So understanding the contiguity type could help into optimizing the performance. Okay, so for the NumPy matrix operations, there are multiple operations that are very important, and the first one is matrix multiplication. So basically, neural network machine learning is nothing but matrix multiplication. That's it's all about. And how we do that in NumPy, we use NumPy dot AB. Okay, but let me just show you before I go to this part, because here I have some illustrations of memory layout. So this is the first one, and this one shows the performance between both. So here they have close performance with respect to the data that was generated. So for this operation, the C contiguity is a little bit faster than the F contiguity operation. Okay, so going back to the matrix multiplication. So this is the dot product, which multiplies two matrices with each other. So you can use NumPy dot, or you can use the @ symbol. Both, they do the same thing. And this is an example. Here you create an array A and an array B using NumPy dot array. And finally you can do result dot equal np dot A and B. And the same thing you can do it A at B. And you can see now this is the first matrix, the second matrix, and it results both into the same value. We can do also eigenvalues and eigenvectors. Do you remember this? Yeah. So this is pretty much simple with NumPy. You can create a matrix A np dot array, and you can extract the eigenvalues and the eigenvectors using np dot linear algebra. So this is the linear algebra package. Okay. Dot eigen of A. So it will return both the eigenvalues and the eigenvectors. This is the example of execution. The eigenvalues are 5 and 2. And you know what is the eigenvalue? It's just you have the matrix AX equal to lambda X. Okay? And this is very important in several applications. So in data science, we use this for dimensionality reduction. Do you remember what is dimensionality reduction? It serves for what? I taught you this last week. We reduce the dimension of the data. Why? What is this process is called in the data science life cycle?
Cleaning of data? Cleaning of data?
No.
Feature.
Feature extraction. When you have a lot of data, some of them is relevant and some of them is not relevant. Okay? So we use feature extraction. And one of the techniques to use feature extraction is principal component analysis for reducing data. It's already in the textbook I've shared with you. They will provide you examples. And you will have a full lecture about feature extraction, because this is very important. And this is used for reducing the data dimension while preserving important information to enhance data analysis and efficiency. This is like the first thing that we do in machine learning. If we have a lot of data, we select what is more relevant, what actually affects the output. We don't want something, if you make machine learning and you include the name of the student in your feature, this is not a feature. The name doesn't affect the performance of that student. That's an example. And in deep learning, it's used to, eigenvalues helps in network initialization and the learning rate optimization. This is one of the important things that we need to do before training machine learning, is to optimize the learning rate and also initialize the networks. So the last thing for today is the singular value decomposition. Do you know about this? Singular value decomposition. It means you have a matrix and you decompose this matrix into 3 distinct matrices. And these matrices, they have some characteristics. So it will be what? Yeah, the first one, U, is an orthogonal matrix consisting of eigenvectors of A transpose. The second one is called sigma. It's a diagonal matrix containing singular values, which are the square root of eigenvalues. And V star is the conjugate transpose, where V is orthogonal matrix of eigenvectors A transpose and A. So this is pretty much used in solving linear equations and also PCA and signal processing. And the implementation here, you just need to use np.linearalgebra.svd of A. And this is going to provide the U matrix, the sigma matrix, and the V transpose matrix.